Hey, students, in this video, we'll discuss some few more radiation properties like what is meant by antenna beam width, beam area, and when we derive what is the relationship between beam area and directivity, and we'll discuss another parameter called beam efficiency, sweep factor, and another parameter front to back ratio FBR, and antenna resolution and radiation distance. So these are all the various antenna parameters we will discuss in this video.
Now we'll discuss another parameter called antenna. Antenna beam width. So antenna beam width can be expressed in two ways. One is in terms of BWFL. It is BWFL width. Beam width between us. Between first widths. Between first widths. Second one is half power beam. Power beam width. Power beam. Okay. So what is meant by this half power being with the being between first nuts? Okay, so see here, see this diagram. If you observe in this diagram, okay, so this is polar part representation, and this is okay. So this is the major. This is the major power. This is the major radiation. Okay, so and this is first side. This is my first side. Okay, and this is called as null. What is meant by null? What is meant by null? What is meant by null? Null means the portion where we don't find any radiation. Null means the portion where we don't find any radiation. So let us take. So let us take, for example, this is the radiation. So this is my radiation pattern. This is the maximum radiation. This is my maximum radiation. Okay. So this is my maximum radiation. Okay, this is my maximum radiation. So, for example, this is the direction of null. This is the direction of first null. Okay, what is meant by null? In this all these directions, in this direction, in this direction, in this direction, the radiation is present. But what about this direction? There is no radiation. Okay, the angle or at which the no radiation is available, that is called as null. That is called as null. Okay, this is first null. If you observe here, this is your second null. This is your second. This is this is your second null. Okay. So the angle subtended between the first nulls, the angle subtended between this first nulls is called as beam width between first null. Beam width between first, the angle subtended by between the first nulls is called as beam width between first nulls. Okay, this is in the case of linear polar. Similarly, if we consider in the polar plot, we consider in the polar plot. Okay, so the graph will be like this. Okay, so this is the maximum. This is our maximum. This is our maximum, and this is our first term. This is our first term. Okay, so this angle. Okay, so this angle is nothing but beam width between first this angle. band beamwidth between first. This is in the linear part. This is the linear part. What about half power beamwidth? Okay, so half power beamwidth means, coming to the derivations, coming to the formulas, half power beamwidth means, for example, if you take, this is the radiation pattern. Okay, when the power has fallen to, this is the maximum power. Okay, so coming to here, there are two types of representation of radiation pattern. One is power pattern, the other one is field pattern. One is field pattern. For example, here if this is expressed, here the radiation characteristics is expressed in power. The radiation characteristics is expressed in power. Okay, so the definition for half power beamwidth is, the definition for half power beamwidth is when the power has fallen to half or 50% of its maximum value. 50% of its maximum value, we call it as half power beamwidth. So this is the maximum value. Okay, 50%, this is the 50% value. Okay, so if I draw this angles like this, draw the lines like this. Okay, this is nothing but, this angle is nothing but half power beam. Half power beam with when the radiation pattern is expressed in terms of power. So what is the definition for the power when it is expressed in, if the radiation pattern is expressed in power, the definition for half power beam is when the power has fallen to 50% of its maximum value or half of its maximum value. Okay, so that is half power beamwidth. Okay, if, for example, if the radiation pattern is expressed in terms of electrical field, if the radiation is expressed in terms of electrical field or magnetic field, the definition for half power bandwidth is, the definition for half power bandwidth is when the field intensity, is equal to 1 by root 2 times of its 1 by root 2 times of its maximum value. Maximum value is called half power. Is called half power beamwidth. Okay, so for example, if you take this, okay, here this angle subtended is half power. So for example, this is the maximum power. This is the point where the power has fallen to half of the maximum. Okay, this is the point where. So this angle is nothing but half power beamwidth. Half power beamwidth. Okay. So there is a relationship between half power beamwidth and beamwidth, approximate relation. Half power beamwidth is approximately equal to beamwidth between first null by. This is very, very important. Okay, antenna beamwidth is the measure of directivity of an antenna. Antenna beamwidth is the measure of directivity of an antenna. Antenna beamwidth is an angle of width in degrees measured on the radiation pattern, places on a major loop between the points where the radiated power has fallen to half of its maximum value. Okay, so this is definitions for beamwidth between first null and half power beam. So the relationship between half power beamwidth and beamwidth between half power beamwidth is equal to beamwidth between first null by beamwidth between first null by. Now let us discuss another parameter called beam area. Beam area, or the other name of this is beam solid angle. Beam area or beam solid angle, and it is represented with rho A. Represented with rho. So what is the definition of beam solid angle? The beam area or beam area or beam area. The beam area of an antenna is given by integral of the normalized power which is given by the integral of the normalized power pattern normalized power pattern over a sphere 4 pi stereo or a sphere 4 pi stereo. Therefore, the formula for beam area, the formula for beam area sigma A is equal to log 0 to pi. Theta is from, sorry, pi is from 0 to 2 pi. Theta is from 0 to pi. Normalized power m of theta comma pi into d omega. D omega means, what is the formula for the d omega? D omega means sin theta into d theta d. So therefore, the beam area is equal to double integral, that is 4 pi into normalized power n of, sorry, n of theta comma pi into d, very, very important one. So what is the formula for the normalized power? Normalized means, already I discussed, normalized means it is equal to P of theta comma pi maximum by P of theta comma. So it is P of theta comma pi maximum by. So already we had discussed. So this is the formula for beam area. Beam area sigma is equal to rho m into d theta. So there is another formula for beam area that is expressed in terms of, so the beam area of an antenna can be described approximately in terms of the angle subtended by half power points of angle subtended by half power points of main loop in two principal planes. Two principal planes means, what are the two principal planes? Theta axis and phi axis. Okay, so under formula is, it is theta decreasing half power beam in phi decreasing half with stereo. Okay, so this is the other definition of beam area. This is the other definition of beam area. Okay, so beam area or beam solid angle is given by the integral of the normalized power pattern over the sphere of power pattern. Okay, now in the previous case we have bring the relationship between we have got the relationship between directivity and power gain. Now we will bring the relationship between beam area, relationship between beam area and directivity. Beam area and directivity. Okay. Now let us bring the relationship between beam area and the directivity. Directivity. Okay, so what is the formula for the directivity? Directivity formula is equal to P radiated by P average or U max by, oh sorry, so this is directivity is called PD of is max by U of theta comma phi, max by U average or U max by U average. Okay, so let us take, what is the formula for the P average? P average formula is equal to P average for organized to dependence to P radiated by 4 pi R square. Okay, so now let us take, what is the formula for E radiated? Total power radiated is equal to pi is equal to 0 to 2 pi, theta is equal to 0 to pi 2d of theta 5 into R square sin theta d theta d5. Okay, so this is the expression. Okay, so P radiated is equal to P average into 4 pi. Okay, so the expression from this P average, sorry, P radiated is equal to this. From this, what is the formula for P average? P average is equal to P radiated. This is the expression for P radiated. P radiated by 4 pi R square. So it's simply write this double integral into P of theta comma phi into R square into sin theta into theta d phi by, what is the value here? P radiated by 4 pi R square. Since here no R component is there, I can cancel this. I can cancel this. Therefore, P average is equal to P average is equal to 0 to 2 pi. Theta is from 0 to pi. P of theta comma pi into sin theta into theta d phi by 4 pi. By 4 pi. Okay, so therefore, P average is equal to this entire thing. This can be replaced with sine sigma. Okay, so that is our integral of, or you can compare theta is 0 to 2 pi, and theta is equal to 0 to pi. So P of theta comma pi d sigma by 4 pi by 4 pi. Therefore, what is the formula for the directivity? Directivity is equal to PD of theta comma phi max by P average. What is the meant by P average? P average is this one. Okay, so this phi is equal to 0 to 2 pi. Theta is equal to 0 to pi. P of theta comma phi d sigma by 4 pi. Okay. So I am okay. Now in this expression, what I am going to do is I am bringing the speed in theta comma phi max to downside. Okay. So the same expression d is equal to, I will bring this 4 pi upside. Okay. So 4 pi by double integral of, so PD of theta comma phi from numerator to denominator. This that is P of theta comma phi by P of theta comma phi max into d sigma. What we call this? P of theta comma phi by P of theta comma phi, that is nothing but normalized. It is nothing but we know that Pn of theta is equal to Pn of theta normalized power is equal to P by P max. P by P max. So in the place of these two things, the place of these two components, I will replace with normalized power. Therefore, directivity D is equal to 4 pi into double integral of Pn of theta comma phi into d sigma. Okay, so this is nothing but this is the expression for beam area. So okay, therefore this is nothing but beam area. Okay, so therefore the relationship between is equal to 4 pi by sigma. So this is the relationship between directivity D and beam area. Very, very important relation. Okay. So there is another formula for directivity. What is the other formula for the directivity? D is, sorry, there is another formula for beam area. It is theta in half power beam with direction and phi in half power beam with direction. The units of stereo. Okay, so in the place of sigma A, the other formula for beam area is okay. So if you observe here, the what are the units of directivity? Directivity is dimensionless. But here, if you observe here, you are getting steradian, 1 by steradian. In order to rectify this, we know that what is the relationship between steradian and radian? One steradian is equal to 1 radian whole square. Okay, so therefore, I can, since the directivity is dimensionless, I can multiply d is equal from the above expression. D is equal to 4 pi into 1 radian square by theta decrease in half power direction by decrease in half power direction stereo. Okay, so in a complete circle, in a complete 2 pi radians is equal to 360 degrees. Okay, or 1 radian is equal to 360 by 2 pi degrees. Okay, therefore 1 radian is equal to 180 by pi, 80 by pi degrees. Very, very important one. 1 radian is equal to 180 by pi degrees. Therefore, directivity is equal to 4 pi into 180 by pi square into theta decreasing half power, pi decreasing half power. So Another definition for directivity is equal to 41293 by theta decreasing of power by decreasing. So there are two derivations for directivity, and the other relation is d is equal to 4 by sigma. So these are the two important derivations. Okay. So d is equal to 4 pi by sigma a. Sigma a denotes beam area and d denotes directivity. Okay. So we may get problems. Okay. We get problems. They will give that theta decrease of directions value, and this one they will ask to calculate the directivity. Okay. So this is how we will derive the relationship between directivity and beam area. This is the relationship between directivity and beam area. Okay, next we will discuss the other parameter called beam efficiency. Beam efficiency. It is related with sigma m. It is related with the epsilon. What is meant by this? Beam efficiency. Okay. So beam area, generally beam area, sigma A consists of major beam area and minor beam area. Small sigma capital M denotes major beam area and small m denotes minor beam area. Now the definition of beam efficiency. Now the definition of beam efficiency is the ratio of main beam area or main beam area to beam area or major beam area to beam area. Major beam area to beam area. Okay, so therefore sigma m is equal to this major beam area to total beam area. Okay, so this is the expression for beam efficiency. Beam efficiency is equal to sigma major load to total beam area. Okay. So similarly, next another factor is called strain factor. Another one is called strain factor. So what is meant by this strain factor? So it is smaller. Is smaller. Strain factor means small. Epsilon smaller. The previous case, beam efficiency means epsilon capital M. Stay factor means epsilon smaller. It is the opposite. It is the ratio of ratio of minor beam area to beam area to total beam area to total beam area. Total beam area sigma. So therefore, sigma smaller is equal to sigma smaller by sigma. Okay. So this is meant by straight. Right? Straight. So from this it is clear that the value of sigma capital M plus the value of sigma small m is equal to 1. The value of beam efficiency and the stay factor is equal to 1. Is equal to 1. Okay. Next we will discuss another parameter called front to back ratio. Front to back ratio. Back ratio. That is FBR. Okay. So it is defined as the ratio of power radiated in desired direction to power radiated in desired direction to power radiated in opposite direction. Power radiated in opposite direction. Opposite direction, which is the ratio of power radiated in desired direction to power radiated in opposite direction. So therefore, FBR is equal to power radiated in desired direction to power radiated in desired direction to power radiated in opposite direction. Power radiated in opposite direction. So higher the FBR, better it is. Okay, so means if any antenna you want to radiate only in the direction, back load should be very less. Okay, so it is the ratio of this required direction to unwanted direction. Okay, so the higher the how can you get the higher FBR? Higher FBR is achieved by diverting the gain of the opposite direction to the forward or desired direction by tuning the length of parasitic elements. By tuning the length of parasitic elements. So next parameter we'll discuss antenna resolution. Antenna resolution. Antenna resolution. So the antenna resolution is equal to half of beamwidth between half of beamwidth between us. Okay. So for example, beamwidth between first nonce is equal to 2 degrees, then antenna resolution. Resolution which is equal to beamwidth between first nonce by 2. Therefore, antenna resolution is equal to this. Okay. So other formula we can define for you know that the beamwidth between first null by 2 is approximately equal to half power beamwidth. Okay, half power beamwidth. Sigma is equal to theta in half power direction. Beam area is equal to 5 degrees in half power stereo. The same we call it as B with between first null by 2 theta direction. B with between first null by 2 in y direction. So see the okay. Next, another form is radiation resistance. Let us discuss another parameter, radiation resistance. What is meant by this? Radiation resistance. The radiation resistance represents the relationship between total energy radiated from a transmitting antenna and the current flowing in the antenna. So the radiation resistance represents the relationship between total energy radiated from a transmitting antenna and the current flowing in the antenna. Is equal to I square into R squared. Therefore, R squared is equal to I squared.